So thank you everyone to have joined this seminar. So today I'm very pleased to have Audun Skau Hansen, who is gonna give us a webinar on machine learning in electronic structure theory. So Audun is a lecturer in the University of Oslo. He has a background in computational physics, and he's been finishing his PhD on local correlation method for infinite systems recently, and just started as a lecturer in the same university. So Audun, the floor is yours. I'm going to turn off my camera and mute myself. If anyone has a question or something, you can just raise your hand or use the question and answer box as usual. All right.
Thank you. So before I start, I'd like to thank you for the invitation. And of course, a special thanks to Elisa. So this talk is based on what was my trial lecture, which took place only some few weeks ago. And Elisa was actually the one who mentored me in my first period of the PhD. And we shared good memories from the time at the CTCC at the University of Oslo. Now, for the seminar, it will span quite widely and at times get a little bit technical. Many of the developments we shall discuss has happened only during the last decade, and even within this short time span, focus has shifted rapidly. Methods quickly evolve and some become outdated. I would like to avoid the pitfall of going into too much detail with regards to a specific method, result, or technical matter, as many of the examples we shall look at deserves a lecture on their own. What I hope to achieve is to give you a proper framing for this topic, as well as some context and direction, rather than just a snapshot from some likely temporary state of affairs. So let's start with the really big picture. Now, I agree that dandelions are not that large compared to a human, but in a quantum perspective, they are absolutely enormous. From the perspective of an electron, they might as well be infinite. The things we study in chemistry take place across several scales of time and length, from quantum transitions to heat exchange. They commonly include complicated irregular geometries like the ones you find in a molecule, and abrupt changes like phase transitions. This richness is reflected in the many ways in which we study chemistry and makes it especially diverse and rich in overlapping methods and models. Theories come about when scientists observe regularities and trends in experimental data, which allow for generalization and establishment of causal connections. We build trust in these theories when they make correct and accurate high-risk predictions of things we do not yet know. These well-proven theories serve many purposes. We can apply them to study nature in a purely theoretical or numerical way, what I guess you would call armchair science. As pedagogical tools, they allow us to exchange scientific information, and they shape our thinking when we extend them beyond the limits of settled science and use them to build new theories. The presence of many at times overlapping theories in chemistry highlights the fact that several representations of the same reality can be equally valid, yet yield different insights into the same problems. Some people have speculated in the past whether or not aliens would describe nature in the same way as we do, with the same math and theories. This is of course hard to tell, but I think it is at least safe to say that they would be familiar with principles like reductionism and emergence. So reductionism is about picking things apart into their constituents. Dandelion seeds are each unique, but they behave in much the same way, independent of each other. We don't have to study each and every one of them in order to describe how they generally react to wind. When applied to chemistry purely based on scale, reductionism is what brings us to electronic structure theory. The idea is that any system of interest in chemistry is made up of a bunch of interacting identical electrons and nuclei. By dissecting the problem under consideration into fundamental units, the aim, or perhaps hope, is that the behavior of the system as a whole can be predicted from its constituent parts. It is a powerful idea which has given us highly accurate models. It provides useful insight into how the universe works. But chemistry also embodies phenomena that are either technically too hard or perhaps even impossible to relate to these fundamental components purely based on scale. To give you some examples, consider the aromaticity of benzene or the bonding between water molecules. these are emergent properties that do not occur in their constituents, but rather arise collectively from the system as a whole. A clarifying example of emergence may be given in purely geometrical terms, as shown in these illustrations. In all cases, you see a collection of 12 points, but only when considering pairs of points can we talk about their linearities and direction, and only when considering 3 of them together does it make any sense to talk about their angularities. The sometimes contradictory ideas of reductionism and emergence are, as you can see, both heavily represented in chemistry, and could of course be discussed in much more depth and nuance than what I've done here. My aim is, however, just to point out this fact relevant for this seminar. When practicing reductionism, as we tend to do in quantum theory, we should be a little bit careful. A poor choice of constituents may reduce the problem beyond obscurity, or it may even dissolve any meaningful interpretation of the properties we seek to understand. Ideally, for reductionism to provide more insights, the constituent parts should have some physical interpretation or offer some meaning related to the real world in some sense. Now, this lecture is not about the philosophy of science, but rather some quite recent developments at the intersection of 2 very cool fields of research. That's in my opinion. Now, these are, of course, electronic structure theory and machine learning, and I here depict them as 2 neighboring trees. Scientific theories and ideas are in some ways like trees, with roots in history and branches in unexpected directions. Sometimes they get entangled in other trees. I'm sure you get the comparison. Electronic structure and machine learning are 2 distinct worlds, each a comprehensive body of theory, which has intersected nicely here in the red area of the leaves, at least for the last decade or so. Actually, the most interesting developments, again in my opinion, have taken place only within the last 5 years, and my impression is that the best is yet to come. So while electronic structure theory has historical roots dating back a century, machine learning in its current form is rather new on the stage, although several of the methods we ascribe to it has been around for some time. In this regard, I'd like to point out that in this regard, I'd like to point out that chemists have been doing machine learning for some time already. Chemistry has this taxonomical side to it, as apparent from the adaptation of words like conformation or species. You notice this quite quickly if you move from physics to chemistry due to the chemist's extreme attention to detail. In physics, we often seek simplicity by means of generalization and reductionism, and tend to poke fun of chemists for their thick books filled with exceptions and special cases. Classification in chemistry is about grouping elements and compounds together according to their structural and functional properties. Over the years, vast databanks of such information has been accumulated. And quite naturally, people have tried to extrapolate and interpolate the properties of unknown compounds from these datasets. In chemistry, this endeavor is often referred to as chemoinformatics or chemometrics, and has roots back as far as the 70s. The reason I'm mentioning this is because these are essentially machine learning methods. Pattern recognition, multivariate curve fitting, clustering, and classification all fall under the umbrella which we today label machine learning and artificial intelligence. But even straight out neural nets have been used in chemistry as far back as the 90s, perhaps surprisingly, since it's only the last decade or so that these methods really have spearheaded notable advances across the natural sciences. I included this paper to illustrate this fact. At any rate, it shows that machine learning is nothing new in chemistry, and that it serves an important purpose, although we have not yet made any direct connection to electronic structure theory. So in broad terms, machine learning are methods devised to perform certain tasks, such as classification, which is to put proper labels on input data. A typical example would be to collect a number of images of cats and dogs where you train your network to correctly classify the animals accordingly. Regression is to determine a certain mapping from a set of inputs to its corresponding output. Some might call this curve fitting, but we could just as well call it modeling. Clustering, finally, is to group similar things together. Now, in the context of machine learning, key to all of these is the fact that where you would traditionally use the computer to input problems into a pre-programmed set of rules to provide the answers, machine learning instead analyzes a set of problems with known answers in order to give you a set of rules. In this way, machine learning, in a sense, constitutes a new programming paradigm. We often distinguish supervised learning from unsupervised learning, where we by supervision refer to a situation where we train our computers to reproduce some data or behavior of interest. In a sense, if you make nature the supervisor, I guess it would be fair to call supervised learning the ultimate modeling tool. This is also the approach which is most relevant in today's seminar. So let's have a closer look. A supervised learning model can be envisioned as a function that takes in some data and some parameters and returns the results as shown in equation here, 1 here. X is the data, Y tilde is the output, and the set of alphas are the parameters. The challenge in supervised learning is then to choose the parameters in such a way that the model reproduces some known data to the best of its ability. The Y without a tilde is of course the data we want the network to reproduce. We can measure this ability with a so-called cost function in equation 2 here. Or you could call it an objective function. In this case, the cost function is a residual norm, which is only 0 when the model perfectly reproduces the data. Minimization of the cost function can be done in several ways, but most commonly uses a mean value of the gradient for a randomly selected batch of cases, the so-called stochastic gradient descent. These models can be many different mathematical constructs. There are very often sequences of matrix products and biases, like this simple one-layer setup you see here. The parameters are put in the matrix there on the left, and the biases are in vector form in the middle, these ones. As you can see, the data is here reduced from 4 x values in vector form to 3 y values, also in vector form. Thus, the parameter array is a 3x4 matrix. With more than one matrix product, you get a so-called multi-layered or deep neural network. Networks are often represented using graphs, as you can see on the right here. The color coding is meant to show how these representations equate, and it is basically the same thing. So this ReLU function you see on the left here, it's called a rectified linear unit. It's where some of the magic takes place. Activation functions such as ReLU comes in several flavors, and they make the network nonlinear. For this reason, networks with more than one layer can support an immense range of functions, which is why we call such networks universal approximators. Now, I included a quote there because I suspect more mathematically inclined amongst the audience will be skeptical of a gradient-based method. It is basically some words of wisdom from some mathematicians that warns us of using gradient descent in the context of linear optimization. This is because we know these methods to be not very efficient or reliable. With a large number of parameters, you would, however, like to avoid doing linear optimization such as Newton's method or anything involving higher order derivatives of the network with respect to the parameters. The problem is, of course, dimensionality and memory demands. Now, gradients may not be the optimal way of minimizing the cost function, but they surely work, and being stochastic, they even enable this approach to avoid local minimums to some extent. Also, there are several more refined versions available using momentum and similar tricks, and they are all well adapted for usage with GPUs and hardware acceleration. So the success of these methods has been due to several factors. First, I would like to say they are extremely versatile and fast in evaluation. So when you have optimized and trained your network, using it to produce results is remarkably cheap. Secondly, The availability of huge datasets has become very common, and we can learn a lot from these kinds of data. Many companies like Google and Facebook are extremely interested in this technology for this reason. Finally, and perhaps on a side note, there has been a very successful marketing campaign involved there. Maybe not intentionally, but still the same. You find competitive websites devoted to challenges for making the best fit, like Kaggle, and the software has been democratized in packages like Keras, TensorFlow, and PyTorch. This democratization of the tools is something quantum chemists and scientists in general should take inspiration from. Now, there are, of course, also many limitations. I'm somewhat new to this, but I did a little experiment on my own using TensorFlow. What you see here is a deep neural network trying to reproduce a simple Gaussian distribution. I trained the network using data only from this region in the middle, where it says training region, and then I use it to extrapolate outside the confines of this region. As you can tell, neural networks may be universal approximants, but they are not especially good extrapolants. I'm sure if I built some more knowledge into this network, it would be able to achieve a perfect fit, but I simply wanted to make a point that we shall return to later on. Now, electronic structure theory is, simply put, the theory that describes the behavior of electrons in the presence of external potentials and each other. It naturally branches directly into chemistry, since its main actors are the electrons interacting on a stage built of nucleons and external fields. It's arguably the most accurate chemical theory devised for dealing with structure at a molecular scale. While we do not know how to solve this problem exactly, while we do know how to solve this problem exactly, the bad news is that we do not possess the computing capabilities to do it for most realistic molecular systems. Neither should we expect to anytime soon, because the mathematical complexity of the theory scales exponentially with the number of electrons in the system. It is like we have the ingredients for a cake, which is impossible to actually make, containing 10 million eggs cooked at 15,000 degrees Kelvin in a 5-dimensional frying pan. It is a bit off-putting. For this reason, quantum chemists have become experts on locating computational bottlenecks, conjuring up approximations, writing highly efficient code, and cutting any defensible corner. The theory has its historical roots firmly planted in the conception of many-body theory 100 years ago. It would be interesting to know how electronic structure theory would have looked had it been discovered in the age of machine learning. Now, I'll try to refrain from conjecturing on what did not happen or what could have happened. But in order to better understand how machine learning methods fits into the electronic structure picture, let's take a little historical dive. Electronic structure theory can be derived as a special case of the general many-body problem in quantum theory, where the possible states of a quantum systems are found as solutions to the time-independent Schrodinger equation. I included the time-independent version of the Schrodinger equation for many interacting particles here in this slide in equation 6. Many of you are, of course, familiar with it, especially when you truncate to two-body interactions. For those who are not familiar, what we do to solve it generally goes like this. First, we need to determine the expression for the Hamiltonian, the H in equation 5. In the H, this is where we include the energetical terms that define the system, like kinetic energy, repulsions and attractions, external fields, and so on. And then next, still in equation 5, we then go on to determine a function psi, which behaves in such a way that H acting on psi simply yields a scalar times psi. If we succeed, we have found one out of many possible solutions of the equation, with the scalar E being the energy of the solution. The motivation for this formulation of our theory of small particles was the failure of classical theory to explain and predict outcomes of a series of experiments devised early last century. It is not often addressed how Schrodinger came up with his famous equation in the first place. Some of you in the audience probably know how to derive it from scratch, but I've never seen it being done. And I certainly won't risk anything like that during this seminar. As the story goes, however, Schrodinger was, in his own words, deeply concerned about Louis de Broglie's wave-particle duality. And when a student asked him why these wave packets lacked an equation describing their time evolution, he spent 2 intense weeks deriving it. So in a sense, Schrodinger just realized that de Broglie's solution lacked a problem to solve. Both Schrodinger and de Broglie was awarded fame, glory, and a Nobel Prize each for their contributions to our understanding of the universe at the quantum level. Now, in this hall of celebrities, we certainly also find Max Born, who, in addition to being the grandfather of Olivia Newton-John, was the father of the probability interpretation of the wave function. Moreover, he was instrumental to the conception of many-body quantum physics, also in the sense that under his supervision, the Department of Theoretical Physics at the University of Göttingen became a flourishing hotspot for what has been named the golden age of atomic physics in the late 1920s. They drew in people like Enrico Fermi, Werner Heisenberg, Friedrich Hund, Wolfgang Pauli, Robert Oppenheimer, Eugene Wigner, and many others. Born even got a Norwegian scientist tangled up in the many-body problem. In 1926, Born tasked Egil Hylleraas, shown on the left, here, with finding the ground state wave function for the helium atom. Hylleraas was happily accepted the challenge, wrestled the problem for a while, and finally succeeded in solving it. Hylleraas' approach has remained relevant ever since, and it is interesting from the perspective of this seminar because it highlights how the many-body problem appeared prior to the successively refined versions we encounter as students these days. Hylleraas' challenge was basically to come up with a wave function for 2 electrons which satisfies the boundary condition and use the experimental energy for the ground state of helium. Quite a lot was known about this problem at the time, with important contributions from Heisenberg and Slater. This was just 1 year after Pauli concluded, actually reluctantly, that the electronic wave function should obey his 1 fermion per state rule, known as the Pauli principle. In practice, this means that permuting the electronic coordinates in the wave function should change its overall sign, so it is, in a sense, a condition we impose on it. The Hamiltonian was basically the same that we use for molecules today. It contained no relativistic effects and no external fields. As you see here, the terms we use are kinetic energy per electron, the attraction from the nucleus, and the interelectronic repulsion. The latter one being the main root of the difficulties in solving this equation. We have, as we commonly do, assumed that the nuclei are point charges on fixed positions, the so-called Born-Oppenheimer approximation, and we pretend there are no external fields of significance and no relativistic effects. So Hylleraas himself attributed the introduction of the variational principle into the framework to Born. The variational principle comes in many flavors depending on the discipline in question. Concerning the wave function method, however, it simply means that since the energy function is constructed from the wave function and the Hamiltonian is bounded below, any valid guess for the wave function constitutes an upper bound to the true ground state wave function. For those unfamiliar with this, have a look at equation 8 here. If it sounds slightly familiar, it may be because this is also how we just treated the cost function of the neural networks. Any set of parameters go, but we are only interested in the ones that minimize the function. Hylleraas' solution was quite different from the determinant-based wave functions with linear combinations of Gaussian orbitals that we use today. And you may find this to be an inviting and refreshing side of electronic structure theory. It means that most people can come up with a valid guess for the wave function, and a way to decide whether or not it's a good representation is to compute the energy. In a sense, it's like a competition. In order to compute this energy, Hylleraas had to, exactly like we do today, use a computer. His Mercedes Euclid is of course nothing compared to our high-performance computing clusters, but it did a trick and produced an ionization energy of 24.35 electron volts, much closer to the experimental value than previous attempts, and it was celebrated as a proof to the validity of quantum theory as a whole. Hylleraas' wave function is an excellent trial function for the 2-electron problem because it supports so well the true shape of the wave function. It is antisymmetric, square integrable, and has the correct so-called cusps at the places where the positions intersect between electrons and the nucleus. Now, while it's possible to extend Hylleraas' approach beyond the two-electron case, it is quite cumbersome and complicated. Thus, when Slater and Fock independently introduced a determinant-based wave function almost simultaneous with Hylleraas, they quickly gained much more traction due to the conceptual simplicity. We can gradually include features in the wave function which lowers the variational energy, thus illuminating how to construct a good trial wave function. This is fairly complicated. This fairly complicated construct ensures antisymmetry with respect to electronic coordinates. And it is also from the single determinant approximation to the wave function that we obtain the conceptual understanding of molecular orbitals. The physical reality of the orbital is, of course, dubious, but as many other frameworks in chemistry, it is still very useful, both as a pedagogical tool and as a logical construct on which to base electronic structure theory. So to summarize, as introduced in textbooks these days, the theory is a refined, consistent and robust framework, capable of predicting the structure, properties, and behavior of atoms, molecules, and matter to an astonishing accuracy. Driven by the rapid growth in computational resources and groundbreaking research, the theory is today routinely used in the exploration of new chemistry. It has opened a world of virtual labs where the quantum world can be explored purely from first principles. Now, how does machine learning fit into this picture? You can picture at least 3 ways that machine learning methods can be integrated into electronic structure theory. First, in the middle here, you could imagine training the network to directly yield the desired quantity, provided input data such as atomic positions, charges, and the number of electrons. The output could be something like energy, properties, or distributions. This approach is perhaps the most straightforward, and we shall look at several examples of where it has been applied. Next, to the left, you could replace parts of your Hamiltonian with machine learning methods. For instance, you could replace the most computationally challenging parts, such as the two-body integrals or the exchange correlation in Kuhn-Sham density functional theory. The inputs would again be atomic positions and charges and so on, or some function of these, such as the computationally cheap core Hamiltonian. Now, finally, to the right, you could replace the wave function ansatz itself with something like a neural net. For this to work, you must be able to evaluate the energy of the ansatz, as well as the wave function itself for a given set of electronic positions. Now, let's have a look at some approaches on how to achieve these things. The delta machine learning method has gained some traction due to its versatility and effectiveness. The idea here is not to simply learn properties from atomic positions and so on, but rather learn the corrections, the deltas of the low-level and high-level methods. The correction is obtained from a so-called kernel-ridge regression network, shown here in equation 12. Note that there are some peculiarities here. The norm of the r's occurring in the Slater-type function here is not simply a distance norm. Rather, it is a function which involves Coulomb matrices of both geometries. What it aims to represent is the difference in geometry of the two systems. The parameters alpha are chosen in order to minimize the discrepancies in the final result for a set of training molecules and are obtained using so-called kernel-ridge regression. You could probably obtain similar results using many other kinds of networks as well. But you can see here in the figure on the left that it manages to quite well support the kind of corrections they are after. In this case, it is simply an energy correction from a semi-empirical OD-MP2 approach towards a more accurate G4-MP2 calculation in Gaussian. The method is versatile since in principle any kind of property can be learned. Furthermore, it is of course efficient since evaluating the model is computationally cheap. Pablo Drau, who has been developing this approach, points out in the cited paper here that differences are more suitable to learn than absolutes, since they generally are very similar in magnitude. This reduces the risk of outliers and increases the accuracy in the predicted values. The usefulness of this kind of approach becomes clear when we consider the vastness of chemical space that computational chemists often have to search through in order to find what they are looking for. In this context, I would like to show you a very nice example where they use machine learning to basically screen the chemical space in order to find some potential candidates, which could then be studied further using traditional methods. So let's follow the pipeline a bit. You start out with a large number of possibilities from which you want to pick out the best candidates. This is the lower left corner here. You then split your sample into a small set and a large set, where the small set is used to train and test your model. As they will tell you in machine learning courses, it is of course important to test your model on a separate set of data in order to avoid overfitting. When you're confident in your model, you then go on to predict the target features you're looking for in the full data set, which finally gives you a screened batch of candidates, presumably with a target property. Now, the beautiful thing about this is that it very carefully utilizes the strength of machine learning methods, while at the same time ensures to some degree that we do not extrapolate outside the training region. This is because the training data is randomly sampled from the same space as we would like to screen. So in a sense, this setup is very true to what machine learning is and is not, and it is of course very efficient compared to the full calculation. Now, eagerness is a human property, and I do not know many people who enjoy waiting for the computer to provide results. Thus, when we bring humans directly into contact with calculations, when we let them interact with it as it unfolds, we typically prefer the computer to be responsive and alert to our directions. Interactive use of quantum chemistry software may in some sense appear excessive, but there is some magic happening when we put a curious human mind in direct contact with simulation. From gaming, we know that they pretty quickly test out the boundary of the simulation and push it to its maximum capacity. They will typically also try to break it in various ways. Interestingly, such approaches has in quantum chemistry led to the discoveries of local minimums in the equations, which was found just because a human tried to move a molecule in some strange orientation. For such exploration and interaction to be smooth and responsive, we need blazing fast software to provide results. Thus, in interactive molecular virtual reality applications, machine learning methods should clearly be used. In general, exploration of potential surfaces may be very well accelerated and supported by neural nets. I added a review paper here, actually from 2011, but still relevant if this is interesting to you. Now, when it comes to performance, Kuhn-Sham density functional theory gives a decent trade-off between performance and accuracy in quantum chemistry and material science. Still, it lacks a systematic path towards the exact results, and there are many proposed functionals intended to represent the exchange correlation part of the Hamiltonian, which fails in some cases and works in others. It appears to be a natural term to replace by a neural net, since I assume we are more interested in the capability to reproduce experimental data and more accurate methods than its mathematical structure. I may, of course, be wrong, in which case I apologize. Anyway, attempts to replace the exchange functional with a neural net goes as far back as 1996. On this slide, you see one of several attempts to do just this, in this case for solid-state DFT. The reason I picked this one is because they are trying to learn the exchange correlation function from simply solving for the electron gas, a system without any nucleus. It is impressive that the network performs so well for some systems without being trained on the actual geometry of the system, but you can see that it fails for benzene here. In the paper, they do not provide a detailed explanation of this failure. Rather, they state that the total exchange correlation energy was not fully consistent with the neural net exchange correlation potential. There are many approaches to doing this, and I've included a recent paper for those interested. A recent review paper for those interested. It's the one on the bottom here. Now, replacing terms in the Hamiltonian is one option, but is it possible to replace the whole Hamiltonian? The so-called Schön-Orb network the most difficult to pronounce method of all in this seminar, constructs the Fock matrix or the 𝙚𝙚𝙚𝙦 matrix from only atomic positions and charges. Now, provided the matrix, the orbitals are only a diagonalization step away. The network is of course trained using a specific atomic basis, and it is based on the assumption that there are blocks in the matrix which will be similar depending on the underlying geometry. The main advantage of this scheme is of course performance and the fact that you actually get orbitals out of it. These can be used with heuristical analysis approaches available to quantum chemists, such as Ladin or Mulliken charge population analysis and bond analysis. Furthermore, and perhaps not as obvious, you could imagine using something like this to accelerate the SCF iteration. While the Hamiltonian itself may not be exact, it is likely to be close to the exact solution. So it should require less iterations in order to reach self-consistency. In this respect, I also added this nice paper by Townsend and Wojciechowski, where they obtain a reduction of about 40% in the number of iterations required by a couple cluster singles and double solver using a neural network to prepare the initial guess. Now, both the property-wise and Hamiltonian-wise approaches are kind of risky, since you in many ways lose track of the error in your calculation. The way scientists like Hylleraas in the early 1900s approached this problem was not to attempt to change the problem into something else. They did not make changes to the Hamiltonian as far as I know. Rather, they tried to come up with a mathematical construct, a trial function, that spanned the required Hilbert space to accurately represent the true wave function. Could a neural network take the place of the trial wave function? There are actually several approaches that do just this, and they have all been used within the context of quantum Monte Carlo methods. Let's briefly recap the theory before we go on to some examples. In variational Monte Carlo, the energy of the trial wave function is approximated with a Monte Carlo integral shown here in equation 13. Using importance sampling, that is, sampling from the distribution obtained from the wave function itself, the evaluation of the variational energy becomes simply a sum over discrete samples of the wave function. In order to achieve this, you would typically start out with a random distribution of samples and do a probabilistic random walk, where a move is accepted if the probability in that point is higher than what it was prior. I won't be able to discuss this in detail, but it is called Metropolis-Hastings algorithm for those interested. Now, doing some algebra, we arrive at what is called the local energy, shown here in equation 15. The local energy will yield zero variance when the trial wave function is an exact eigenstate of the Hamiltonian. You can realize that if you replace the Hamiltonian with its eigenvalue. The trick then is, in light of machine learning methods, becomes to let the network take the place of the trial wave function, whereby stochastic gradient descent can be used to minimize the result. First example of this I want to show you is quite elegant, but also a little bit unfamiliar from a quantum chemistry perspective. Now, what they do is actually exactly what we just discussed, but they map the molecular Hamiltonian onto another kind of system using a so-called Jordan-Wigner mapping. They then optimize the trial function, modeled as a network of so-called Boltzmann machines. Now, for an example problem, the dissociation of a carbon dimer, as we can see that the results are pretty close to the full CI solution, closer than you would get with the couple cluster singles, double parentheses, triples. The computational scaling is also slightly unfamiliar, but in the paper they report a sample size of about 100,000 samples. Next up, there is the deep learning wave function ansatz called Paulinet. Here we have a lot of heuristics put into the model, as you can see on the schematic here on the left. We have both a multi-reference Hartree-Fock component. We have a Jastrow factor with a special component for cusps and backflow. These components are color-coded, so all reddish elements in this figure are trainable neural networks optimized using stochastic gradient descent. This network has been shown to give close to exact results for up to 30 electrons with a computational complexity of only the number of electrons to the power of 4. And as you can see, the results are rather impressive. The blue points there are Paulinet, for what I presume is a representative selection of systems. The y-axis is the percentage of correlation energy recovered by the ansatz. And you can see Paulinet performed quite well in this regard. Now, when I say there is a lot of heuristic that goes into this trial function, I'm talking about all the ingredients, which in a sense limits the search in Hilbert space and focuses it down to the relevant subspace where we expect to find the wave function. Such limitations may of course be the model, may of course make the model more efficient, but at the same time we build more assumptions into it. If we instead leave these choices up to the training of the neural net, we end up with something like Ferminet. Ferminet is also a neural network ansatz, but this time we have not much more than the assumption of antisymmetry built into the model. This means that it requires more parameters to properly minimize the energy, but it is at the same time conceptually simpler. In order to point it in the right direction, it is explicitly given also the distances between the electron coordinates and nuclei, which helps the network to figure out the cusp condition. Now, comparing to CCST parentheses T at the bottom line, we can see here in the figure to the left that Ferminet captures quite nicely the ground state wave function. So returning to the bigger picture, replacing the energy or property calculation with a neural net may have its usefulness, especially when it comes to screening of large chemical spaces and responsive codes in interactive interfaces. There is, however, the problem of reliability, because you would basically have to trust that the training data can be extrapolated or interpolated to the exact systems you're studying. As we have seen, machine learning methods do not extrapolate nicely. There is also more to modeling than just reproducing data. So while neural network does a great job when it comes to performance, it is hard for humans to learn anything from the final weights and biases in the optimized model. In this sense, it is reductionism, only that the reduced units are totally incomprehensible to us. It's just numbers. For instance, I'm sure you could train a neural network to simply add numbers together. What would it mean then if it had a success rate of 99.99%? Would we be able to deduce anything from the neural net's weights and biases about the operation of addition? This is, of course, my personal opinion, and clever people are working on how to interpret the networks. But I do not believe that neural nets will replace our analytical theories anytime soon. We need them as pedagogical tools and to fill in blind spots in our scientific knowledge. The prospect of replacing the Hamiltonian is also slightly scary from a reductionist view. When you introduce small discrepancies in the Hamiltonian, what you are doing in reality is to change the system. This means that the wave function you produce, say the orbitals of the approximated Fock matrix, are actually the solutions of some slightly different problem. Personally, I'd like to have an approximate solution to an exact problem, not an exact solution to an approximate problem, if that makes sense to you. Still, since these methods can significantly reduce the number of iterations required by the optimization routines, I believe they can be useful as accelerators alongside these or quasi-Newtonian approaches. This way, we can use them without worrying about actually losing any accuracy in our calculation. The idea of replacing the trial function with a neural net is definitely my favorite. The reason for this is that in reality, when looking back to the time of Hylleraas and his contemporaries, we have not really advanced our understanding of the mathematical structure of the wave function that much. You may not agree, and I do not mean to underestimate the many valuable contributions from quantum chemists and physicists over the last century. But the reduction of the wave function into a bunch of Slater determinants, built from molecular orbitals, built from linear combination of atomic orbitals, does not really reduce the wave function into understandable, physically comprehensible quantities. Yes, I understand that the molecular orbitals provide some insight, which is in many cases used to correctly predict structure. But if a single Slater determinant was physically meaningful, we would probably not need all of these correcting terms. So perhaps we're better off just accepting that these functions are hard to model, and that something like a non-linear neural net, a universal approximator, is the way to go. Some would argue that as long as we can evaluate the function and its energy, we have all the information we need. The development for using neural nets as trial function has occurred just during the last 5 years or so. I'm curious for what is to come here, especially in light of what goes on with quantum computers, which is a story on its own terms. And with these speculations regarding the future, I will conclude this seminar. I'm impressed about what has been achieved by people in this field. While we have still a way to go, I would not be surprised if it turns out that we are currently at the onset of our own golden age, the golden age of quantum machine learning. I hope you also found this presentation refreshing. Thank you for your attention.
So thank you, Audun. Is there any questions or remarks? No, then I don't see any. Then I do have a question. So, well, first, yeah, I guess you have all the literatures here. Could you come back to this Pauli net and Fermi nets?
Yes. Which one of them?
The one, yeah. Could you, like one slide before, I think?
Yes, yes.
Yeah. So, I mean, here you say that you have these blocks, if I understand correctly, which are like all trainable, the pink ones?
Yes, yes.
And so how in practice does it work? Do you train all of them together? Can you train each of one independently of each other? How much control do you have on this?
So I don't know the exact details of how they do this. I wouldn't speculate on how they actually do this. But if you compare to, say, this Fermi net, in this case, you have a much simpler setup, right? So you don't have all these different kinds of parameters clustered into different networks, kind of. So in this case, it would be much simpler to train. I'm not sure whether they train separately one of these and then optimize. Of course, there must be some kind of complicated interreliance between all of the parameters in this model.
Because here you said that you can have a multi-reference Hartree-Fock baseline.
Yeah, yeah.
Because I mean, that is one big problem with most methods that we have in electronic structure, is that usually single reference is doing okay, but then you can't port that towards multi-reference methods.
Mm-hmm.
Do you think these methods would be able to do that?
So I'm not really sure how this all mixes together. And I'm not sure whether anybody has some clear idea of how much of the Hilbert space you span with these kinds of different constructs. I guess it becomes much harder to analyze, especially since you have these nonlinear functions. But if you replace these things, I mentioned those slightly, just briefly earlier, this universal approximation theorems. And they address just this aspect of it, how well you span the space you want to represent. What kind of support does these different functions have? So I'm not sure what happens when you mix a multi-reference Hartree-Fock state with all these other kinds of trainable parameters. It's really complicated.
Okay, yeah. Well, I guess it's really the beginning that we see in this field.
Yeah.
So it's difficult to say where it's going to go, but
Right.
there is definitely a lot of potential.
Yeah, so I mean, like I just brought in these two networks. There are more work being done on this, but I brought in these two because they represent, for me, they represent two kinds of extremes. In the one sense, you bake a lot of like your traditional knowledge of how the wave function should look, right? You have the Jastrow factor, you have the backflow, and you have a lot of things going into this. So you assume a lot about the wave function, and in the other case, you don't do that at all. So you try to assume as little as possible. You just give it the charges and the differences in the electronic coordinates, and then it's supposed to figure it out all by itself. And there are ups and downs of both approaches. I guess this is more conceptually simpler to do.
All right. Well, I don't see any other questions, so I think we can thank you once more for this lecture, and I'll say goodbye to everyone then.
Thank you.
Thank you, Audun.